You know that perfect golden brown, crispy bite of fried food? Of course you do. We all love it. But have you ever stopped to think about what happens to all that oil left in the deep fryer? It turns out there's a really fascinating scientific story happening in there. One that connects your favorite restaurant to some seriously advanced material science. So, let's dive in. And just to give you a sense of the scale we're talking about here, restaurants in the US alone throw out over 1.2 billion pounds of used cooking oil every single year. That is a staggering amount of waste, and it's a huge headache for the food industry. And this gets us right to the heart of the deep fryer's dilemma. You see, the very same intense heat that gives us that perfect crunch is also, at the same time, systematically destroying the cooking oil. It's turning a precious ingredient into a waste product. So when does good oil actually go bad? Well, frying oil has a whole life cycle. It starts in this break-in stage, where the food comes out kind of pale and not cooked right. Then it hits that sweet spot, the optimum phase, where everything is perfectly golden and crisp. But that perfection doesn't last. The oil starts degrading, food gets darker, greasier, until finally it hits the runaway stage. At that point, it's totally useless and has to be tossed. Now, this whole breakdown, it's not just about the oil getting dirty with little bits of food. No. It's a fundamental chemical transformation happening right there in the fryer. The mix of high heat, the air, and even the water coming from the food itself sets off this chain reaction, changing the very molecules of the oil. So let's meet the chemical culprits responsible for this mess. So what's really going on down at the molecular level? Inside that hot fryer, what is it that's attacking the oil and turning it into something you really don't want to eat? It really comes down to a three-pronged attack. First, you've got hydrolysis. That's just a fancy word for the steam coming off the food, literally ripping the oil molecules apart. Then there's oxidation, because the hot oil is reacting with oxygen from the air. And finally, you get polymerization. This is where all those broken molecules start linking up, forming these long, sticky chains that make the oil thick, foamy, and dark. Yuck. Okay, so it sounds pretty bleak for our cooking oil, right? But what if we could actually fight back against this chemical attack? Well, this is where a special class of materials called adsorbents comes into play. Think of them like a microscopic cleanup crew, designed to go in and pull all the bad stuff right out of the oil. Now, notice I said adsorbent with a D, not absorbent with a B. It's a really important difference. An absorbent soaks things up like a paper towel, but an adsorbent, its power is on its surface. It has this incredibly porous, textured surface that acts like molecular Velcro, grabbing onto impurity molecules and trapping them. And there's a whole lineup of these materials. Some are natural, some are synthetic. You've got things like bentonite clay, zeolites, diatomaceous earth, and probably the most famous one, activated carbon. These are all used to filter and basically regenerate used cooking oil. Let's take a closer look at how this actually works. What you're seeing here is the molecular structure of bentonite clay. See all those layers? It's that complex, porous structure that gives it the power to physically grab onto and hold those nasty breakdown products floating around in the oil. So, we have these powerful, sometimes pretty expensive materials like activated carbon to do the cleaning. But the real breakthrough in this story, the real twist, comes from a much more humble and honestly a totally unexpected source. I mean, think about this for a second. What if you could use a massive stream of agricultural waste to solve this huge industrial waste problem? This is where the simple, everyday rice husk comes into the picture. It is one of the most abundant agricultural byproducts on the entire planet. So some scientists had this brilliant idea to test raw, completely untreated rice husks as an absorbent. And the results? They were absolutely stunning. This quote from their research really says it all. This super low-cost, incredibly common waste material performed just as well as the expensive, highly processed stuff. Let's put them side by side. Look at this. In terms of reducing acidity, they both hit the exact same mark, 63%. But here's the real kicker. It took less than half the amount of raw rice husk to do the exact same job as the activated carbon. So it's not just as good, it's actually more efficient. And it costs next to nothing. So, raw rice husk is already a surprise hero. But the story doesn't stop there, not even close. Scientists then asked, okay, this is great, But can we make it even better? Can we turn this simple waste into a true super adsorbent? And they came up with this amazing 3-step power-up process. First, they char the husk, basically carbonizing it. Step 2 is the real magic. They use a special solution to wash out or leach the silica ash that's naturally inside the husk. This totally opens up its internal structure. And finally, they activate it with another chemical, creating this vast, incredible network of tiny pores. If you were to look at the raw char under a super powerful microscope, you'd see this. It's a dense, non-porous surface. All that cleaning potential is locked away. Its pores are just clogged up with ash. But after their treatment, bam, look at that. The surface is completely re-engineered. It's now this complex, almost honeycombed structure, just full of these perfectly formed micropores. It's now primed and ready to trap everything in its path. And the data just speaks for itself. The raw char started with a surface area of about 28 square meters per gram. But after the full treatment, that number just skyrockets to 645 square meters per gram. That is a more than 23 times increase in its cleaning power. It's unbelievable. Just let that number sink in for a minute. 645 square meters per gram. To put that into perspective for you, a tiny pinch of this stuff, an amount you could easily hold in your hand, has a surface area as big as a football field. That is an incredible feat of material engineering. So what we've just seen is just a perfect, beautiful example of a circular economy in action. We're taking a super low-value agricultural waste product, and through some really clever science, we're turning it into a high-value solution that solves a completely different industrial waste problem. And that really leaves us with a final, fascinating question to think about. This whole incredible discovery came from somebody looking at a pile of discarded rice husks and seeing potential. It just makes you wonder, what other stuff that we call waste is just sitting around waiting to be revealed as a resource in disguise?